With the partial derivatives we've been talking about, we've only really considered two directions, parallel to the x-axis and parallel to the y-axis. Let's change that. Let's look at derivatives in any direction. And to illustrate this, let's start with the same function that we used in section 14.4. So we had 5 minus x squared over 9 minus y squared over 4. And we looked at the point 3, 2, 3. So we can go ahead and plot that. So f of xy is equal to 5 minus x squared over 9 minus y squared over 4. And we had this elliptic paraboloid. I'm going to make that color a little lighter. Makes things show up a little bit nicer. And 3, 2, 3 is a point on the surface. Why are you doing that? There. Alright, so we looked at what happens if we take slices through our surface that are parallel to our x and y axes through that point. What if we pick, say, a vector like, I don't know, negative 1, 3. So I'm going to make a vector. It starts at A, but then moves from A in the direction of negative 1, 3. And I'll put a 0 there because it's 3 dimensions. So we have this other direction. And in fact, we could even go ahead and put in the plane through that direction. Of course, GeoGebra is going to make that a little bit tricky for me because it doesn't like to allow me to make planes through using vectors. So I'm going to make a line through point A in the direction of vector u. And I'm also going to make a line through point A in the vertical direction. So I'm going to give it the vector 0, 0, 1. And I can then go ahead and use those two lines to give myself a plane. So I have this plane through that point that it's a vertical plane that cuts through my surface. And that plane intersects my surface in a curve. And let's make that a little bit darker so you can see it better. So we have this curve, and that curve is going to have some derivative. And we'd like to know, can we find out what that derivative is? Well, one thing we can do is to look at the line through the point 3, 2 in the direction of our vector v. So if our v here is the direction negative 1, 3, then we could use the vector notation for that. R of t is our point 3, 2. We're ignoring the z component because we want to see what happens as we change the x and y, and the surface itself is going to deal with the z. But we take our point 3, 2, we add some parameter t times the vector. Or we could go ahead and combine all this into one vector here. So we have 3 minus t and 2 plus 3t. This is our x, this is our y. That if we go ahead and actually plug those into the function, and say f of, we can even put f of r of t to kind of write it simpler, but we're replacing x with 3 minus t, and the y with 2 plus 3t. And then this is a function of t. How about we differentiate it? If we differentiate this with respect to t, what happens? So I don't really want to write f prime here. Maybe if I renamed it something, if I call this like g of t is this thing, then I can do that. But the derivative of this function, of this composition with respect to t, obviously the 5 goes away. We have to use the chain rule technically here, so we end up pulling out the negative 1. So we get a positive 3 minus t times 2 over 9. And over here, we pull out a 3, but then we also have the 2 from the power, so we have 6 times 2 plus 3t over 4. And if we then say at our point, 3, 2, which, well, that corresponds to t equals 0. If we plug t equals 0 in here, well, here we have 2 times 3 over 9, which just becomes a 2/3. And this becomes a 6 times 2 over 4, which becomes a 3. Or in other words, we get a negative 7/3. That's the derivative of that function. Unfortunately, there is a slight issue here. We were concerned with the direction of v, but the magnitude of v actually ended up changing our result. Negative 7/3 kind of isn't what we were looking for. If we looked at the vector, say, if we looked at w equals negative 2, 6, and we did the same thing, we would end up with negative 14 over 3. So here w is the same direction. I just multiplied v by 2. That doesn't change the direction. And I end up multiplying the derivative that I got from this process by 2 as well. So in order to make everything work nicely and consistently, we're going to first insist that instead of just working with any vector, we're going to work with unit vectors. Or at least we're going to turn our vectors into unit vectors before we actually do this process. In this case, our unit vector, we take v and we divide out by its magnitude, which just gives me the vector negative 1, 3 over the square root of 10. And that will give me an answer, and this is the one that we will want in the future once we actually write out our definitions. I'll get the answer of negative 7 over 3 square root 10. And you can rationalize that however you want to. I'm just going to leave it that way. But the point here is that we did actually get an idea of what the slope should be for this curve. And in fact, that is exactly what slope we should have for this curve. So let's give a notation and a name to this thing. We are going to call this the directional derivative of our function at this point. And specifically, if we're talking about a direction that's given by a unit vector, it's d sub that unit vector applied to our function, and we just use our normal limit definition for the derivative. Just instead of putting x, inside here, for our partial derivative in the x direction, we would put x naught plus h, and then just leave y naught by itself, versus with our partial derivative in the y direction, we put y naught plus h, and then have the x naught by itself. Here we actually modify both the x naught and the y naught by whatever proportion we have from our unit vector. It's essentially what we're doing here is we're replacing what we have inside of the f with the parametric equations for our line. This is the same formula that we had back here, except we're using a unit vector. One thing to note, that if we are working in the direction of I, so remember I is our vector that's 1, 0, it's in the x direction, then really all looking at is the partial derivative of f in the x direction. And the same thing with j. J is the vector 0, 1. It's just the y direction. And the directional derivative in that direction is just the partial derivative with respect to y. So this is not really a completely new thing. All the stuff that we've been working with up to this point has been a special case of it. But it'll turn out that we can actually make use of most of the stuff we've been doing with partial derivatives to work with this new kind of derivative. And that's actually what we want to do. The first thing we want to do before we try to do anything more with this, since we don't really want to work with limits if we don't have to, let's actually derive an easy formula for the directional derivative. I'm going to go ahead and do that by defining a new function. I'm going to say g of h is equal to this first f. So this is f of x naught plus ha, comma y naught plus hb. This is a function of a single variable h, and its derivative at, well, if we differentiate it at 0, what do we get? Well, we have the limit as h goes to 0 of g of h minus g of 0 over h. That's just the definition of the derivative at 0. If we go ahead and replace those with what they are, solve the limit as h goes to 0, but g of h was this thing. And g of 0, well, if we plug in 0 for h, we just have x naught and y naught. So we have f of x naught, y naught. And of course, that the whole point of this is that we just get the directional derivative in the direction of u of our function at x naught, y naught. So what we've done here is we essentially created a function of one variable whose derivative 0 is just the directional derivative that we're looking for. However, we can actually view g as a composition. So if we say z is equal to f of x naught plus h, well, actually, let's just do z is equal to f of xy. Here, x is equal to x naught plus ah, and y is equal to y naught plus bh. And that means that g of h is the composition that happens when we plug these functions into this function. In other words, if we write out our tree diagram, z depends on x and y, but then x and y both depend on h. And so if we want to find out what the derivative of z is with respect to h, we think about, well, we go down this route or we go down this route. We have the partial derivative of z with respect to x times the derivative of x with respect to h plus the derivative of z with respect to y times the derivative of y with respect to h. But the derivative of z with respect to h, the whole point of that is that that's really looking at the function g. So we are just looking at the derivative of g at 0. So I'm going to go ahead and just rename this to g prime of 0. The partial derivative of z with respect to x, well, the z is just the function f. So really we're looking at the derivative of f with respect to x at our point. The derivative of x with respect to h, this time we can actually do the derivative. X is just a linear function of h. Hopefully it shouldn't be too hard to see that the derivative of x naught plus ah is just a. A is just a constant here. And then we do the same thing over here. Partial z partial y is just f sub y of x naught, y naught. And then this one, we're now differentiating y naught plus bh, so we get a b. So g prime of 0 is this formula in terms of the partial derivatives of f. But g prime of 0 was the directional derivative that we were looking for. Therefore, we have this result. Basically, we can always find the directional derivatives, assuming here that we do have a differentiable function. That was something that was kind of subtle in here where we didn't actually address it, but technically this only really works if we do have a differentiable function. We'll kind of not worry too much about that part. But if we do have a differentiable function, then the directional derivative in the direction of any unit vector is just given in terms of that unit vector and the partial derivatives of our function. So that's why we've been focusing on the partial derivatives so much. We don't really need to calculate the directional derivative directly most of the time. The only times we would have to is if we don't have a differentiable function, in which case we could have derivatives in various directions and not every direction. In some ways, you can say a differentiable function is one where all of the directional derivatives exist. Let's look at an example of this. Here we have a function e to the x times sine of y. We have a particular point that we're concerned about, and we want the directional derivative of the function in the direction of negative 6, 8. So first thing we could do is go ahead and calculate our partial derivatives, because we're going to be needing those. So derivative of e to the x sine of y in the direction of x, there the sine of y is a constant, so we just differentiate e to the x and we still are at e to the x. Same thing with y, this time the e to the x is a constant. The derivative sine of y is a cosine of y. And of course, we are mostly interested about these partial derivatives at the point 0 pi over 3. Of course, e to the 0 is a 1, so that's not too interesting. But the sine of y, that's where we have to actually pay attention. Sine of pi over 3 is root 3 over 2. And this time we get to take the cosine of pi over 3, which is 1/2. Okay, so do we take those and we multiply by the components of v? No, we have to turn v into a unit vector first. This is not a unit vector. So take the magnitude of v. Yeah, the square root of 6 squared plus 8 squared. That's the square root of 100, or just 10. That means our unit vector, which I'm going to go ahead and call u. We take negative 6, 8. We divide it by 10. And while we might sometimes leave it in this form, the fact is that we need the components of this vector. So we're going to go ahead and just divide the negative 6 and the 8 with the 10. Negative 6 over 10 is a negative 3/5. 8 over 10 is a 4/5. So our directional derivative is our derivative with respect to x times our first component of u plus the derivative with respect to y times the second component of u. And if you want to simplify that, we can make it what? So this will give us a 4 over 10. Wait. Oh, I see what I did. This should not be a 2. That should be a 5. So everything's going to be over 10 in the long run. But I'll have a 4, then minus 3 square root 3. Let's actually go ahead and plot this thing. So recall our function here, f of xy, is e to the x times sine of y. So we get this thing. It will be a little clearer from this direction. We're looking at a point. That point is 0, pi over 3, but we do need the z value here. If we plug in our 0 and pi over 3 into our function, we just get the point square root, well, we get the value of square root 3 over 2. And let's, again, make this a little bit lighter. I feel like that makes it a little easier to see. But we just have this point here. All right, there, that's a little bit better. But I'm going to go ahead and I'm going to plot in my vector. So I have a vector starting at A in the direction of -6. Let me -6, 8. That comes off in a particular direction. It doesn't really tell us a slope there, so that's why we need to actually use the value that we got. I'm going to go ahead and make a line. Actually, yeah. I'm going to go ahead and make a line using the curve function. So it's going through that point. So I'm going to go ahead and use the formula x naught minus at, or plus at, where my a here is the negative 3 over 5 that comes from my vector. Then we have pi over 3 plus 4/5 t. So here I'm using the fact that I have 0 and then pi over 3 as my x naught and y naught. Then my z value at that point is square root 3 over 2, and then I need to add my derivative times t. So remember my derivative was 4 minus 3 square root 3 divided by 10, and then that's times t. And the variable's t, and I just like to use -10 to 10. And so we have this line. Maybe I'll make that darker. Make it stand out a little bit better. We have this line. And might be a little hard to see, but that line is a tangent line to that surface in the same direction as our vector. That's exactly the tangent line in that direction. It has that slope of 4 minus 3 square root 3 over 10, and it passes through that point. It's exactly what we wanted it to be. So that's the advantage of being able to do all this stuff. We actually can find tangent lines in whatever direction we want, not just in the x and y directions. Of course, there's nothing stopping us from doing the same kind of definition in 3 dimensions. So here, the directional derivative of a function of 3 variables in the direction of some unit vector a, b, c is just given in the same way, except now we just have a z component as well to our functions. We can even do this in much more generality in all dimensions, just using our vector notation. So here we're using x naught as the vector x naught through whatever. So in 2 dimensions this would be x naught y naught. In 3 dimensions is x naught y naught z naught. But it's just playing the role of that vector. And then what we have in the other one is just that x naught plus the multiple h of our unit vector u. It's the same definition. It works exactly the same way. It's just using vectors. And in fact, doing any kind of calculations can be done exactly the same kind of way using the partial derivatives. So I can find the directional derivative of a function of 3 variables by taking the partial derivatives with respect to x, y, and z and multiply them by the components of my unit vector. So all we end up having to do is take partial derivatives. That's why we've been spending so much time on partial derivatives without even talking about these other ones. So let's do an example in 3 dimensions. So here we have a function of 3 variables. They're not x, y, and z, they're r, s, t instead, but that's not really an issue. We're looking at the point 1, 1, 1, and we have a direction, a vector, of 4, 12, 6, written in terms of I, j, and k. We'll start off by looking at our partial derivatives. Partial derivative with respect to r. Well, now we're dealing with a natural logarithm, so we're going to have to use the chain rule here. The derivative of the natural logarithm is 1 over what's inside of it. So we end up with 1 over 3r plus 6s plus 9t. But now we need to multiply by the derivative of the inside. The derivative of 3r plus 6s plus 9t with respect to r. Well, the 6s and the 9t don't matter. Derivative of 3r is 3. If we go ahead and plug in 1, 1, 1, we have 3 on top, and the bottom is 3 plus 6 plus 9. That's 18. Or in other words, we get 1 over 6. Do the same thing for s. In fact, a lot of the process is exactly the same because we are just differentiating the logarithm again. But this time the derivative of the inside is going to be a 6. So we can go ahead and plug in 1, 1, 1. The top is still 6, the bottom is still 18. And so now we get a 1/3. Finally, we look at t. This time the derivative of the inside is a 9. And so we have 9 over 18, or 1/2. So we have our partial derivatives, but we want the derivative in the direction of 4, 12, 6. Of course, that is not a unit vector, so that's the first thing we need to do, is turn that into a unit vector. So magnitude of v, we have the square root of 4 squared plus 12 squared plus 6 squared. If we work all that out, we get the square root of 196, which maybe that's a little outside the range that most people recognize immediately, but that is the square root of 14, so we get 14 out of this. That means our unit vector u, if we divide all these by 14, 4 over 14 is 2/7. 12 over 14 is 6/7. And 6 over 14 is 3/7. So our directional derivative in the direction of u of this function at the point 1, 1, 1, we take let's go ahead and do the 1/6 from our partial derivative with respect to r times our first component of 2/7. Then we have 1/3 from the directional derivative with respect to s times our second component. And then we have the 1/2 from t and the 3/7. If we work all this out, it's a fun little calculation, but we get 23 over 42. So while we can't really view this as necessarily a slope, I mean, we could if we could work with 4 dimensions, but since we can't do that, we just kind of have to think about this as representing the change, the rate of change if you start at 1, 1, 1 and you move in the direction of this vector at a unit speed. That's what this represents. How quickly does the values of the function change as we move in that direction? Alright, so I'm going to go ahead and leave this video here. There is There are some other things we can talk about, and we will actually bring up another way of looking at computing the directional derivative in the next video. So I'll see you there.